Welcome to Math TV with Professor V. This is video lecture for section 9.5 on the dot product. This video lecture belongs to the Precalculus video lecture series. I'll link a video right here if you need the dot product explained for multivariable calculus. All right, definition. If we have vector V equal to a1 I hat plus b1 j hat, remember that bold I and j refer to our unit vectors. So I hat is the unit vector with components 1, 0, and j hat is the unit vector with components 0, 1. I say hat because when we write it out, we don't try to write it bold, right guys? Okay, good. And then w is the vector a2 I hat plus b2 j hat. So we have these two vectors, v and w. The dot product, v dotted with w, is defined as the following. v dot w equals a1 times a2 plus b1 times b2. So notice you take the horizontal components of each vector, multiply them by each other, and then to that you would add the vertical components of each of the vectors multiplied by each other. Notice the result from dotting two vectors or finding their dot product yields a scalar. And for that reason, sometimes the dot product is referred to as the scalar product. So this is one way to multiply two vectors. There's another definition for multiplying vectors, which you'll learn later, and the result yields another vector. So keep it straight, dot product yields a scalar quantity, not another vector. Also, if you go on to study more mathematics, in particular multivariable calculus, you'll revisit the dot product, and this definition still holds for vectors that are in three-dimensional space and dimensional space. All right? Excellent. So now let's look at some examples and compute dot products. We have here two vectors, v, with components 2 I hat minus 3 j hat. So I'm going to rewrite v as follows, just so I can focus on the components. So let's rewrite it without the unit vectors I hat and j hat. V is the vector 2, negative 3, and then w is the vector 5, 3. So let's find all of the following quantities. First one is v dotted with w. So be careful when you're writing out vectors yourself by hand. You don't try to sit there and write it bold, right? You just put the little arrow above the letter to indicate that it's a vector. Now, v dotted with w. So look at the definition here. You're going to take each of the horizontal components, or the components that come in the first portion of the vector. So we have 2, and I'm going to multiply that by 5, and to that I'm going to add the product of the vertical components. So this would be negative 3 times 3. And then what do we have here? This is going to be 10 plus negative 9, or 10 minus 9, which is 1. And that's it. That's the result. So v dot w is equal to 1. All right, in part B, we're asked to find w dotted with v. Do you suspect it will be different? Do you think the dot product is commutative? Well, take your guess, and then we'll see right now. So w dotted with v, so I'm going to take 5 times 2 and add to that 3 times negative 3. And I get 10 plus negative 9, so 10 minus 9, which is 1. So, same result. That means, and you can investigate this further, the dot product is indeed commutative. And if you think about it, it makes sense, because what operations are involved when you compute the dot product of two vectors? Multiplication and addition, right? And both of those operations are commutative, so it makes sense the dot product should be as well. All right, part C is asking us to find v dotted with itself. All right, so since you can't see v, I'll just rewrite it here. So v is 2, negative 3, and then I'm going to dot it with itself. Notice when you're writing a dot for the dot product, Make it a heavier, more solid dot so we know it's different than the normal multiplication symbol that we use for scalar quantities. So you're going to take product of horizontal components, 2 times 2, plus product of vertical components, so that's going to be -3 times -3. And what do we have here? This is going to be 4 plus 9, so 13. Lovely. All right, example D asks us to find W dotted with itself. All right, so W was the vector 5, 3, and I'm going to dot it with itself. Sounds good. So you take product of horizontal components, so that's going to be 5 times 5, and to that we will add product of the vertical components, so that will be 3 times 3. And what do we get? We get 25 plus 9, so 34. Very good. Now, next part is just a little bit of investigative exploratory fun. So E asks us to find the magnitude of vector V. All right, so remember vector V had components 2, -3. And in the previous video lecture, we went over finding the magnitude of a vector. So remember, it's the square root of the sum of the square of its components. So we would have square root of 2 squared plus -3 squared. And what does this give us? This gives us square root of 4 plus 9, so rad 13. Interesting, because notice in part C, we found V dotted with itself, and we got 13. And then now when we're finding the magnitude of V, we get square root of 13. Okay, we'll look at that a little further shortly. And then last thing, part F asks us to find the magnitude of W. So let me refresh your memory. W is the vector with components 5, 3. So magnitude of W would be square root of 5 squared plus 3 squared. So what will that be? Square root of 25 plus 9, rad 34. My goodness. Look at, when we dotted W with itself, we got 34, and then magnitude of W is rad 34. That is not just a coincidence. So here we go, people. Properties of the dot product. If U, V, and W are vectors, then boom, commutative property. We already talked about this. U dotted with V is equal to V dotted with U. So the dot product is commutative. Okay, later on, you might have to prove it. You can't prove it just by plugging in specific numbers. Math doesn't work that way. Okay, then we have the distributive property. So U dotted with the sum of two vectors V plus W is equal to U dot V plus U dot W. This is nice. And then property 4, you guys, we just noticed this. If you dot a vector with itself, it's equal to the magnitude squared. Ooh la la. And then the 0 vector, right? Remember the 0 vector has 0 for all its components. So if we're in two-dimensional vector space, it would be just the vector 0, 0. If you dot it with any vector V, you get back 0. Notice this one's a scalar because it's not bold, right? Scalar. This 0 here is a vector. Yes, people, love it. Okay, so one thing that the dot product is especially useful for is finding the angle between two vectors. All right, so we have the following. If U and V are two non-zero vectors, then the angle theta, where theta is going to be between 0 and pi, between U and V is determined by the following formula. So cosine of theta is equal to u dotted with v divided by the magnitude of each of those vectors. So the magnitude of u times the magnitude of v. And then in the end, to figure out the angle theta, you would just do cosine inverse of the quantity on the right-hand side. All right. Good. So we will be using this formula quite frequently right now to figure out the angle between two vectors. And let's introduce some new terminology. We say two vectors v and w are orthogonal if and only if v dotted with w equals 0. So if the dot product between two vectors is 0, that means cosine of theta, right, would also equal 0. Cosine of the angle between those two vectors would be 0. And we know that cosine is equal to 0 when theta is pi over 2 or 90 degrees. Okay, so basically when we say two vectors are orthogonal, that means that they meet at a 90-degree angle. However, we have to be a little bit careful because notice here, this definition still holds for the 0 vector. The 0 vector dotted with any vector would give you 0, the scalar. And the 0 vector, you could say it has no specific direction or it takes on all directions. And we do adopt the convention in saying that the 0 vector is orthogonal to every vector, even though it doesn't meet a vector at a 90-degree angle, right? Okay, so if this is the first time you've heard the word orthogonal, you could think of it as essentially the same thing as perpendicular or normal. These are all terms that mean meet at a right angle. It's customary to refer to two vectors as being orthogonal. We talk about two lines and say that those are perpendicular, and a line to a plane or a vector to a plane is referred to as normal. It meets it at a 90-degree angle. However, we can still use the term orthogonal when we're talking about the 0 vector, all right, even though it doesn't meet another vector, technically at a 90-degree angle, all right? Good. And then now that we've talked about orthogonal a whole bunch, we can say that two vectors, v and w, are parallel if there is a non-zero scalar, we'll call it alpha, such that v is equal to alpha times w. And in this case, the angle theta between v and w is either 0 or pi. 0 degrees or 180 degrees. So look here. If I have two vectors, v and w, v has components 3, -1, and w has components 6 and -2, it's pretty easy to see that if I just double the components of v, I end up with w, right? So we could write that 2v is equal to w. And that is essentially what alpha is. I mean, in the definition, alpha is in front of w. So if you want to be all matchy-matchy, you could say v equals 1/2 w. Whatever, it doesn't matter. There's a constant that we can find to multiply one of the vectors by to end up with the other vectors. That's what it means to be scalar multiples of one another. Now notice, since the signs match up, like the sign of both first components is positive and the sign of both the second components is negative, then the angle between these vectors is 0. They're pointing in the same direction. 3, -1, and 6, -2. Let's graph it really quick, just so you can believe it in your heart of hearts. So 1, 2, 3, 4, 5, 6. Okay, and then here's -1, here's -2. So we've got 3, -1. Remember these, I'm going to draw these as position vectors. There's 3, -1. And then 6, -2 would just extend further, same direction. I want it to look better. This 3, -1 should go just a wee bit lower, shouldn't it? Okay, let me draw 6, -2 first. Oh, lovely. There's 6, -2. Here's 3, -1. Bam. So notice W is just double vector V, and they're pointing in the same direction. All right. Now, if instead we had V, let's leave it as 3, -1, and then W was -6, 2. What would change? Well, then W would be pointing in the opposite direction, right? This way. And that would mean the angle between them would be pi, or 180 degrees, okay? They'd still be scalar multiples of each other. It's just in this case, alpha would be negative, right? Since the sign switches from one vector to the other. All right, good. So when they point in opposite directions, then the angle between them is pi, or 180 degrees. If they point in the same direction, it's 0. Lovely. Okay, so let's look at some examples here. We're going to find the dot product between these two vectors, find the angle between them, and then state whether they are parallel, orthogonal, or neither. So first one, we have vector V with components 3 and -4. And then vector W with components 9 and -12. Okay, so first part says find the dot product V dotted with W. After a while, you're going to do these in your head, right? So we have 3, -4 dotted with 9, -12. So that's 3 times 9 plus -4 times -12. So what do we get here? That's 27 plus 48, yes. Good, good, good. And we end up with 75. Okay, that's part A. Done. Part B, find the angle between V and W. So, time to bust out our handy dandy formula. Cosine of theta equals V dotted with W over magnitude of V times magnitude of W. Well, we already have V dot W from part A, right? So we got 75 in the numerator. Then we need magnitude of V times magnitude of W. So magnitude of V is going to be square root of the sum of the square of its components. So that would be 3 squared plus -4 squared. And then magnitude of W, similarly, square root of 9 squared plus -12 squared. Okay. Good. So now let's see what we got going on. Cosine of theta is equal to 75 over, oh, I love it, square root of 3 squared plus -4 squared. That's going to be square root of 9 plus 16, which is 25, is it not? And then square root of 9 squared plus -12 squared, that's square root of 81 plus 144. What is that? Why, yes, it's 225. And then we end up with now 75 over square root of 25 is 5, square root of 225 is 15. Why, yes, it's 75 over 75. So this means cosine of theta is equal to 1. When does cosine equal 1? When theta is equal to 0 radians or 0 degrees. Okay, same thing. So to answer the question for part C, are the vectors parallel, orthogonal, or neither? These two vectors are parallel. Okay, and you actually could have seen that from the get-go, because remember, V was the vector 3, -4, W was the vector 9, negative 12. And check it out. To get from V to W, all you would need to do is multiply each of the components by 3, right? So we could write W equals 3V. And since they're scalar multiples of each other, bing, bing, boom, you say that they're parallel. So you don't need to use the formula that we used in part B. I just did it because I'm an obedient math student, right? So when the directions tell you to do something, you do it. That's how you do well in math. All right, let's look at another example. There was part 2 here. Do you see it? Yes, V is I hat and W is negative 3J hat. So let's just rewrite it. Oh, look, I already did it. So V has components 1, 0, and W has components 0, negative 3. So for part A, let's find their dot product. So V dotted with W is going to be product of the horizontal components, so 1 times 0, plus now product of vertical components, 0 times negative 3. And what do we get? We get 0 plus 0, which is 0. Voila. All right, part B. Find the angle between them. Maybe you can already tell the dot product 0. That means these two vectors are orthogonal. The angle between them is 90. Well, that's true. Let's just use the formula to see how it all comes together. So cosine of theta, remember, is V dotted with W over magnitude of V times magnitude of W. We already know the dot product is 0, so we got 0 in the numerator. Magnitude of V is just going to be 1, right? Because you have the square root of 1 squared plus 0 squared. And then similarly, magnitude of W is going to come out to be 3, because you have square root of 0 squared plus negative 3 squared. So this is 0 over 3, which is still 0. When is cosine of some angle equal to 0? Remember, we restrict theta to be between 0 and pi per the definition. So that means theta is equal to pi over 2 or 90 degrees. Okay, you didn't have to do all that though. As soon as you notice the dot product 0, this is going to be the result that follows. So part C was asking whether these two vectors are parallel, orthogonal, or neither. And what would you say? Yes, they are orthogonal. Very good. Okay, last one I threw in, because we got to see one of each, don't we? It just didn't feel right to only do 2. Okay, it just didn't feel right. So we have vector V with components 1, negative 2, and W with components negative 7, 15. All right, why don't you pause the video, give this one a shot on your own. Okay, so find their dot product, find the angle between these two vectors, and then state whether they are parallel, orthogonal, or neither. I'll give you a moment. Okay, did you do it? I hope you did. That's how you can see if you really understand what's going on. Okay, so V dotted with W, I'm going to take 1 times negative 7 plus negative 2 times 15. So this is negative 7 minus 30, which is negative 37. Beautiful, beautiful. Did you get the same thing? I hope so. All right, B, let's find the angle between them. So cosine theta, I just rewrite the formula every single time. That's a good tip too. If you're trying to memorize stuff, the more you write it out, it'll get embedded in your memory. So V dot W, we have that from part A, negative 37, over magnitude of V. So let's see here. Where's vector V? Where did you go? Right here. 1, negative 2. So magnitude is going to be 1 squared plus negative 2 squared. And then I need magnitude of W. W is right here. Okay, great. So that's negative 7 squared plus 15 squared. Okay, so now we have cosine theta equals negative 37 over what's going on in that denominator. This is 1 plus 4. Okay, so we've got square root of 5 plus square root of 49 plus 225, which is 274. Let me double check. 49 plus 225. Yes, beautiful. Okay, you can multiply those by each other if you want. So this would be negative 37 over square root 274 times 5 would be, we have rad 1370. I mean, we're going to need our calculator in a hot second, so that step's sort of unnecessary because you can just find theta by doing cosine inverse this mess or this mess. Just be careful with your parentheses when you're entering that quantity, but I mean, your calculator can compute all that for you, right? So you don't have to clean it up excessively. Anyways, I'll just do this one. It has less keystrokes since we actually figured it out, but the first time I did it, I didn't bother multiplying out the denominator, okay? For this one, it would make more sense to give your answer in degrees, okay? But just check with your instructor. The directions will usually state how much to round to, if they want degrees or radians, all right? As soon as I notice the dot product's negative, it should be a clear indicator that the angle between the two vectors is going to be greater than 90, right? Because cosine's negative in quadrant 2 and 3, and we're not talking about angles that are going to be in quadrant 3. So we're in quadrant 2 of our unit circle, yes, which means the angles are bigger than 90 degrees. Okay, so if we round to about 2 decimal places, this is going to be approximately 178.45 degrees. All right, or if your instructor wants radians, usually they don't. It's 3.11 radians. Okay, good. So part C, are these vectors parallel, orthogonal, or neither? They are not parallel, they are not orthogonal, they are neither, whatever you say. Okay, fabulous. Now, let's look at how to decompose a vector into 2 orthogonal vectors. And the reason that we do this is because we have a lot of physics applications that involve vectors, and this is going to be essential. So typically when we're working in physics with vector quantities, one of the applications that we can use is finding work or force and see how it's being applied in certain circumstances. So that's why these vectors are called F for force. So say you have a force, in this case, it would be the force of gravity. Notice it's pointing directly downward. And we oftentimes want to decompose it into 2 vectors that are orthogonal, okay? We, in the last section, looked at how to decompose a vector into vertical and horizontal components, right? So that means you take a vector, you project it along the x-axis and the y-axis. Now we want to just project it into any arbitrary direction with the components being perpendicular to one another, orthogonal, okay? Notice here, so we have vector V. We've projected it previously into a horizontal and a vertical component, and that's essentially what we're doing here. We're just rotating these 2 axes into whatever situation is necessary. Okay, so how exactly are we going to do this? Well, say you have 2 vectors, V and W, they're non-zero vectors, then the vector projection of V onto W is defined as follows. So V1 is the vector projection of V onto W. Later in your math career, you'll write this as the vector projection of V onto W, like so. And it's equal to V dotted with W divided by the magnitude of W squared. So this is all a scalar, and then you multiply that by the vector W. So the result is going to be a vector. That's why it's called a vector projection. Where this formula comes from, you can read about on your own, or if you end up studying multivariable calculus, you'll see more detail, okay, or in your physics classes. Now, the decomposition of V into V1 and V2, where V1 is parallel to W and V2 is orthogonal to W, is given as follows. So notice vector V1 here, that was our original projection of V onto W, right? And then V2 is the orthogonal projection of V onto W. So you'll see that written later on as the orthogonal projection of V onto W, like so. And the way you find it is you just take the original vector V and subtract V1, which is the vector projection of V onto W. I know it's so confusing, so much terms, and it feels really crazy, but it's actually not that wild when you sit down and do some examples. Okay? Good. So let's decompose vector V into two vectors, V1 and V2, where V1 is parallel to W and V2 is orthogonal to W. All right, don't be scared. Here we go. Let's just rewrite the vectors without the I's and J's because I feel like things are wild enough as is. So vector V has components -3, 2, and vector W has components 2, 1. All right, they want us to find V1. V1 is parallel to W. It's the vector projection of V along W. I think maybe the V1 and V2 notation is just a little cumbersome because later on you just write it out, you know, using that notation, which is a little more clear. Okay, so we're gonna take V dotted with W, divide by the magnitude of W squared times W. So V dot W, good thing we practiced this dot product sufficiently. We're very professional at it. V dot W, -3 times 2 plus 2 times 1, divided by magnitude of W squared. So that means no radical, right? You're just going to take 2 squared plus 1 squared. And then I'm going to multiply all of that by vector W, 2, 1. Oh, now it's not so bad. So what do we have in the numerator? -3 times 2, that's -6, plus 2. In the denominator, we have a 5 times the vector 2, 1. -6 plus 2, that's going to be -4/5 times 2, 1. So what do we get? This is going to be -8/5 and -4/5. Beautiful. Or if we want to write our answer using the unit vectors I hat and j hat, that would be -8/5 I hat minus 4/5 j hat. Okay, and since they gave me the problem using the vectors I hat and j hat, I'll write my final answer that way as well. Okay, so this is the vector projection of V along W. And then, what else do they want? They want the orthogonal projection of V along W, which we're calling V2, per this book's definition. So to get V2, all you do is you take your original vector V and you subtract the projection of V along W, which we're calling V1. Okay, so it's V minus V1. Where's V? V was -3, 2, and I'm subtracting what I just found here. That's V1, all right? So subtracting -8/5, -4/5. All right, and then when you subtract vectors, remember you just subtract corresponding components. So this is going to be -3, actually plus 8/5, and then 2 plus 4/5. So what do we have? That's -15/5 plus 8, so -7/5. 2 is 10/5 plus 4/5 is 14/5. Okay, or -7/5 I hat plus 14/5 j hat. Beautiful. Okay, good, good, good. A wagon is pulled horizontally by exerting a force of 20 pounds on the handle at an angle of 30 degrees with the horizontal. How much work is done in moving the wagon 100 feet? Okay, so we have to have a brief discussion on work. If you've already taken some physics, great. If not, this is just going to be a really brief overview to get you to where you can actually solve the problem. Okay, if you want more in-depth though, you can do some reading on your own. So to compute the work done by, notice here, a constant force, which I'll call F, in moving an object from A to B. This is defined as follows. We say that work is equal to the magnitude of that force times the distance from A to B. Okay, so let's use some notation. Work is equal to the magnitude of the force. And then think of it this way. You're moving it from point A to point B, right? So the distance would be the magnitude of the vector AB. Ooh la la. Okay. Now, in this definition, it's assumed that the force F is applied along the line of motion, in the direction of motion. However, notice here that the direction of motion would be forward, right, parallel to the ground. But the force is not being applied in that direction. It's being applied at a 30-degree angle with the ground. So what do? So if the constant force F is not along the line of motion, but instead is at an angle theta in the direction of motion, then the work is defined as follows. So to compute work, it's equal to the force dotted with vector AB, okay? And you can see this comes from figuring out the magnitude of the vector projection of F onto AB. That would be this here, times the distance, so magnitude of AB, and everything ends up simplifying to this quantity here. So this is what we're going to use. Work equals force dotted with the vector AB. Okay, so let's see what's going on here. We have this sweet little girl pulling her wagon. And I'm going to draw everything out here on a coordinate system. Okay, X, Y. And the problem told us we're going to move the wagon 100 feet. So I'm going to put point A, the starting point, at the origin. Okay, and then the wagon's going to move 100 feet. So point B is going to be at 100, 0, right? And A is at 0, 0. So we need that vector AB. So AB would have components 100, 0. Do you guys agree? Oh, good. Okay, and then this is the force F here, indicated by that arrow that the girl is applying when she's pulling the wagon. And the force F is 20 pounds. Okay, so here's force F. Magnitude of F is 20, and this is a 30-degree angle here. Okay, so remember, as we've studied before, we can decompose F into vertical and horizontal components. You take its magnitude times cosine of 30 and sine of 30. So we have X component, Y component. So this is going to be 20 times cosine of 30 is rad 3 over 2, and sine of 30 is 1/2. So this is going to give us 10 rad 3 and 10. This is the horizontal component. This is the vertical component. Okay, so now we're ready to roll. Work equals force dotted with AB. So work is going to equal F dot AB. Where's F? Right there. 10 rad 3, comma 10, dotted with AB, which has components 100, 0. 10 rad 3 times 100, 1000 rad 3 plus 0. So don't need to write it. So let's just put some units on here. Work is going to be in foot-pounds. Why is that? Well, the force is in pounds and the distance is in feet. So you just multiply them and bam, there's your new unit, foot-pounds. Not my favorite unit, but whatever. It is what it is. I like joules better. It sounds classier. Ooh, things are just not wanting to get boxed today, huh? Don't box me in. Here we go. Or 1000 times rad 3 is approximately 1732 foot-pounds. Okay, that's it. How do you feel? The physics applications can be a little tricky, intense, but you know, it's necessary. When you study mathematics, you must do some physics. So give this video a thumbs up, subscribe if you haven't already, and stay tuned. We've got more to come.